I'd like to introduce Saul. We can go into the presentation. Just give me a minute. We'll have Paul pull the presentation up for DC Water, and we'll start in on that. And I think Saul is on the line, I believe. Sharon?
Yes,
Okay.
I'm here. Can you hear me?
Yes, Saul.
Great.
And let me, Saul, just give me a second, and I'm just going to say a few words about Saul. And I think we can get into, we'll get you there in virtual and right here in Westboro, Massachusetts. So, boy, that was a quick trip, Saul, hopefully. You heard Saul's name mentioned this morning several times as some of the projects that have been done. These are actual projects that have been operating. So Saul, as a major wastewater utility, saw an opportunity here and was one of the pioneers certainly to try to pull all the pieces together. So with that, I'm not sure.
Okay, thank you very much. Thank you to Massachusetts for inviting me to present today and for putting together this program. Sounds like I'm really missing out by not having been there for lunch. So I'm very sorry I couldn't attend in person, but I'm gonna talk today about our efforts at DC Water with respect to wastewater thermal energy. I'm not going to go into any details on sort of how. I'm assuming that was covered very well this morning. Obviously, if there are questions about that sort of thing or any details, happy to talk about that. But we're going to focus on two elements here. First is the two installations that we have operating in Washington, D.C. today. The other is some data that we collected prior to those installations that gave us pretty good confidence about the likely success of the system. Before I get into the meat of the presentation, I need to give a quick disclaimer. Certainly, we're very happy to appear as part of an event with private companies, vendors, the like. But we do want to make clear that DC Water, as a governmental authority, does not endorse, recommend, or otherwise partner with any particular vendor unless we explicitly say so. And for the in the case of wastewater thermal, we have not done that. So we're happy to appear with them. We think they have good information to present, but it's not something that we are specifically recommending. Okay, DC Water, we are one of the nation's largest utilities. We provide retail drinking water and wastewater collection services within the boundaries of the District of Columbia to its residents and visitors. We also provide wholesale wastewater treatment service, not only to the District of Columbia, but to many of the surrounding counties as well. As a result, we have one of the largest wastewater treatment plants in the world, and for the level of treatment we provide, it is the largest in the world. There is no plant that is both larger and doing a higher level of treatment. We have an excellent track record. Generally speaking, the utility, I think, has a good reputation. I don't want to brag too much about the work that we do, but if it's helpful, I can say that certainly I have almost nothing to do with it. I develop projects and don't really do much with operations. It's all thanks to my colleagues who do a great job keeping the wastewater plant running and keeping the water flowing. All right, wastewater thermal energy. So hopefully everybody by now from the morning session is familiar with the concept. We are using the wastewater in the sewer system as a neutral temperature reservoir that allows us to efficiently heat buildings in the winter and efficiently cool buildings in the summer by reducing the amount of electricity that is needed to drive a heat pump. There are two such systems operating today in Washington, D.C. Both have been operating for almost 6 years. Both started quite coincidentally in the same month, February of 2018. One is a private commercial office building. It happens to be the headquarters of the American Geophysical Union, which occupies either one or two of the floors. They also own the building. The rest is commercial leased office space. In the case of this building, we were approached. They wanted to be the first net zero energy building in Washington, D.C. And in fact, they are the first net zero energy building in Washington, D.C. And they were looking for essentially anything they could do that would reduce the amount of energy the building would consume. The solar canopy that provides energy and allows them to be net zero was strictly limited in size due to historic district rules. And as a result, they could only they were very strictly capped on their energy generation and the potential, even with the battery and maxing out as much as they possibly could on site. So they were looking to absolutely minimize essentially every aspect of energy consumption in the building, and that of course includes thermal energy and HVAC. We were involved as the local water utility. We were contacted about what, could we help? Was there anything that was there? And it just so happened that at the time we were working on the early stages of wastewater thermal, and we suggested that it might be something worth looking into. We then worked with them to assess the potential viability at the site, and it turned out that luckily for all involved, there was a pretty big sewer running under the sidewalk right in front of the building here on Florida Avenue. So extremely close proximity, plenty of flow, probably 4 or 5 times the amount of flow that they actually needed to heat and cool the building. And, a pretty convenient property setup where they had this little plaza here that provided some space, obvious space to put in underground infrastructure. We then negotiated with them a license. I'm going to talk about the terms of that in a slide or two here. But we negotiated a legal arrangement by which they are able to access the energy, and they then built the system and are now operating it. Challenges for this system. The biggest was the state of the sewer and its depth. This was a 30-foot deep sewer, like I said, fairly large, so important for our system, many people depending on it, and very old. This sewer dated back to the 1880s. Certainly, there are many older sewers. If you go to Paris, 1880s might well be, newest 10%, but in Washington, D.C., this is one of the oldest sewers we have in operation. It was built of unreinforced brick, which is not the best. That means that the mortar that was originally holding those bricks together was long gone, and we were essentially keeping an unreinforced arch supported in part by the weight of the overburden, compressing all those bricks together. Not ideal. Not something we wanted to just go around digging up. So part of the requirements that we put in place included lining the sewer. This was a structural carbon liner that went 30 feet upstream and 30 feet downstream from the proposed point of connection. Absolute requirement for our structural engineering team. We also had some requirements about construction methods. They needed to dig down evenly on all sides. They needed to ensure that they weren't loading the sewer in one way or another as they went ahead and built it. So you can see the end result here, and I'm happy to say to give the result at the end, we did not see any problems in the sewer over the course of this project. They complied with our requirements, and those requirements were sufficient to keep the sewer in good shape. You can see here the old brick sewer has been uncovered, and you can see the liner that's sitting inside the old bricks and forming a new structural sewer. Once that was in place and cured, they dug down, cut open the pipe, and put a side stream. Because of the close proximity, this side stream could be very, very short. We're looking 5 feet maybe of total pipe length, so very convenient there. And then they have a wet well. They're using the Huber system at this site, so there is a wet well with a screen inside it. The wastewater flows in through that screen, fills up the bottom of the wet well, and is then pumped out. The pumped out wastewater flows into the lower levels of the building. They have a heat exchanger in the parking garage. That heat exchanger then provides condenser water to a heat pump stack on the first floor. So very simple setup, certainly very straightforward. Return flow comes back through and into the same sewer. We also have DC Water headquarters. This is DC Water's primary office building, again, completed in 2018. We don't have any technical functions here. It houses our admin, procurement, HR, customer service functions. It happens to be built on top of a sewage pump station. So we had very easy access to a very large amount of sewage flow. And as part of the design of the building, we asked the designer, and in fact, we required them to give us a proposal to incorporate wastewater thermal. Because of the relative ease of connection, it was by far the cheapest option for a high efficiency thermal energy supply. And we were able to make that connection to the main wastewater flow that is going through the pump station underneath the building. Certainly much simpler from a civil standpoint than the American Geophysical Union. We didn't have to dig, we didn't have to cut open a sewer, nothing like that. We really just took a side stream off an already existing pipe, connected it up to a heat exchanger, and that's where we get the condenser water for the heat pump for the building. These buildings are using about the same amount of flow. AGU is a little bit smaller, but they wanted to be a little bit more certain about their supply. They have no backup, whereas our headquarters does have a cooling tower as the backup. Looking in a little bit more detail at the main sewer connection for the American Geophysical Union, I know this drawing is a little bit fine to see, but we can highlight some crucial points here. We have an inlet coming out of the sewer going into the wet well and an outlet coming back out. These are coming out of essentially the same connection, but they're a couple feet separated in the pipe, so we should be able to avoid any looping. We have then over here, one of the big concerns we had, because this is a combined sewer, was grit and debris. The screen should do a nice job of handling any debris, especially larger objects, but grit was a major concern. We were worried that their wet well would fill up over time with sand and sediment. So we don't have a strict way we knew would work for that, but what we ultimately decided on, working with the engineers for AGU, was to make the connection just a little bit above the actual bottom of the invert of the sewer. So you have this lip, and it's only a few inches, really, but it's a little bit of lip, and the idea is that the heaviest sand and gravel that's rolling its way down the bottom of the sewer pipe should hopefully stay at the bottom and not come in over the lip there. Is it working? We don't know for sure, but certainly we have not had to come back and pump out the wet well. So, first 6 years of returns look fairly good. The covenant. So our lawyers did some very nice work to create a legal document that gives both the AGU and DC Water the appropriate assurances in order to allow the system to be built and operated. The form of the document is a real estate covenant, so it is literally recorded and attached to the property. The point here is we wanted more than just a contract with AGU. If AGU sells the building or goes out of business or somehow the building passes from their control, this agreement needs to remain in place. And that's because, it is connected to the sewer main, and the absolute requirement for us is to keep that sewer main running. We do not want to have problems for literally thousands of people, if not tens of thousands, who are upstream of this connection point for, just to allow the clean energy to be extracted. So we're attached to the property. The AGU agreed that they would submit all their plans for our approval and follow any, permit-related instructions that we gave them. So we would be able to dictate the design to a degree. They also agreed that they would do the design. So we weren't going to do it. We were going to put in specifications and they were going to meet them. And essentially those specifications were, first, that the design not disrupt or interfere with the flow in the sewer main. And second, that there would be no inlet or outlet of material, that this would be a closed system. And this was important for our sewer operational permit, which we are responsible for EPA. We do not want this to allow this to become a dumping point. So AGU has a completely separate and separately permitted typical commercial office building sewage connection. But if we were going to permit this as some kind of open source, our lawyers had concerns could somebody dump sewage into the sewer this way? Could it become a point for toxic or industrial waste to go in because it's an industrial system? And the way to avoid those concerns and just sort of put them to bed very simply was to say this system must be closed. Whatever comes into the sewer at the end of the system has to be the same as what came out of the sewer, except for its temperature. And of course that met the operational parameters of the system just fine, so it was a very easy thing to agree to. On the other side, we agreed to provide AGU with access to the sewage, which they obviously need in order to run the system. We also agreed that if there was a problem in the sewer, we would restore the flow past their access point as quickly as possible. So we couldn't guarantee that there would always be sewage available for them if there were a problem in the pipe or some other, disruption. But we would agree that we would fix it as quickly as we could. We would let them know if there were any problems. And we also agreed that we would not allow an upstream thermal connection that would have a negative impact on theirs. And this was a bit of a punt. We didn't have any data at the time that could let us know, how far upstream somebody would need to be to mitigate a temperature impact, or what the loss of efficiency might be for how big a system upstream. So we said, we will prohibit an upstream connection that has any negative impact on you, pending your approval. So that was what we were able to agree to, and I think in general it actually went very well, and we were able to get a very good arrangement with them, much easier than I thought it was going to be. I was very worried about the legalities of this, and our lawyers really did a nice job. Okay, DC Water headquarters, much simpler. Obviously, we don't need a legal agreement because it's our own sewage for our own building. But the setup is much the same. We have a heat exchanger, we bring it out, we flow it through. Okay, shifting gears for the second half of my presentation this afternoon, I want to talk a bit about the temperature in the sewers. We were lucky enough to get quite a lot of data in 2015 and 2016 because our engineering department was doing a study of flow to revise their flow model in the collection system. They put about 120 flow meters at various points, and we got lucky in that every one of these flow meters also measured temperature, I think to help ensure accuracy on the flow measurements. But it meant that we had a whole bunch of temperature data, which we were able to have basically for free. And we took that data in, we, got a nice intern to sit down and start going through it and come up with some conclusions and make some nice graphs. And that gave us a very good data baseline to be able to think about how we could make use of the thermal potential in the sewer. So one of the things we found out is that the sewage temperature, especially the patterns of the sewage temperature, were very consistent from point to point. Well, there were some variations. Some places were a few degrees colder or warmer, and there were one or two sort of anomalies, especially where the sewer was underneath a stream. Most pipes followed a very similar pattern. And we have one of those points here that is very representative of the typical pattern up on the screen. So what you can see here is a full year's worth of temperature data from a single point in the DC sewer system. And there's a lot of things that are worth noting about this graph. First, you'll see that it's kind of fuzzy, right? It's not just a straight line. There's kind of it's kind of a thick line. That's because every day we have a thermal cycle. So it gets warmer in the morning, everybody wakes up, and we see this in the flow as well. You get more flow in the morning, but everybody wakes up, flushes, you get a whole bunch of warm water coming out of everybody's house. And then at night, as there's less flow and less water coming down, it gets colder. So we have about a 2 degree Fahrenheit daily cycle just about every day. You'll also see that there's a seasonal cycle, peaking here in the high 70s, minimum here in the upper 50s. So, rule of thumb, maybe we have a 58 to 78 degree Fahrenheit seasonal cycle. Notably, that seasonal cycle is not perfectly aligned with the air temperature peaks and minimums that we would see here in Washington. We see our hottest air temperatures in late July and in August, and the hottest sewage temperatures are actually in early to mid-September. Likewise, our coldest air temperatures are in late December and January, and we see the coldest sewage temperatures here in maybe mid-February. And that's very convenient from a thermal energy perspective because it means you're getting even a few extra degrees of advantage versus what the just sort of top line cycle numbers would tell you. So when you actually have the hottest air temperatures here, you're not at 78, you're at more like 76. So that's an extra 2 degrees of efficiency advantage. Likewise, in the winter, it's even better. January 1st, we're at a balmy 65 in the sewers. We don't get down to the upper 50s for another month or so, which means that we're able to get very high efficiency right when the buildings are at their coldest and need the most thermal energy put in. The other big thing you can see from this graph are the spikes and dips. Those are rainwater and snowmelt coming into the system. DC mostly has a combined sewer system, and even where it doesn't, we have quite a lot of I&I. Our sewers are leaky. That means that we're getting a lot of water coming in at essentially atmospheric temperatures every time it rains. And that changes the temperature. So it's getting warmer in the summer, colder in the winter. And obviously that's going to have an impact. We were very concerned about this when we first started thinking about the potential for wastewater thermal, but a couple of points here and on the next graph allowed us to have more confidence that things would work just fine. First of all, you see that while there are spikes and dips, they're not happening every day, and over the course of the year, there's maybe 60 of them. And they're also very short-lived, right? So you can see here that these spikes, they're not showing up over multiple days, right? In fact, they're shorter than these daily cycles. So these are spikes that are measured in minutes to hours, which means that while you will lose some efficiency when they're happening, over the course of a year, it's not going to be very much. The other important thing is that with all those spikes and dips, you're really not getting outside this 55 to 80 temperature bound, except for this one winter storm. And that's pretty good news, right? 55 to 80 is still going to be highly efficient, and we're really not exceeding that much. So based on this, we estimated that conservatively, we could put a 10 degree Fahrenheit delta T on the source system. If you do the math, that means for every 1,000,000 gallons per day of flow, you have about a megawatt of thermal energy. We have close to 300 MGD of flow, but we figured, in terms of base flow overnight, we'd actually be able to access, say, 200, which means maybe 200 megawatts of thermal energy. If you do the math, that's enough to heat and cool maybe 5 to 10% of the buildings in DC. So that's very good. It's a lot of energy, but it's not a panacea, right? We're not going to heat and cool the whole city with this technology. It is one arrow in the quiver or one tool in the toolbox. It is not the be-all, end-all that completely solves your city's thermal energy needs. But that said, it may well be the best and most efficient of the various options that are out there for those buildings that can take advantage of it. All right. I want to go a little bit more into detail into the effect of rain and snow on our system. And again, we have some very interesting data. This was all collected in February 2015 at one of our larger pump stations. And I'm going to go through this graph in pretty fine detail. First, we can see the water temperature in red up at the top here, corresponding to the axis on the left. This is the sewage temperature flowing through this pump station. And you can see the daily cycle I was talking about. Every day we have about a 2-degree bump in the morning as people get up and flush their toilets. And then we had kind of normal winter temperatures, highs in the 40s, cold nights for Washington, D.C. I'm sure Massachusetts, this would be considered, the best week in January, but for us, this is pretty normal. We then had a cold week. So we had a whole week where the temperature didn't get above freezing even as a high. And that's unusual for D.C. And you can see what happened to the wastewater temperature over the course of that week. It got colder, but not by much. So we went from a 58 to 60 daily cycle to about a 56, 58 daily cycle. So over the course of a week below freezing, we lost about 2 degrees. That's not nothing, but at the end of the day, if you're able to heat and cool out of a 56 or 58 degree reservoir, you're doing very well. You're doing a whole lot better than trying to heat or cool out of 10 degree Fahrenheit outside air, that's for sure. We had some snow on the ground in this period. And then here on the 23rd, all of a sudden we had an unusually warm day where it popped up and we had a high almost at 50 degrees. All that snow melted at once, flowed into the sewer system, and we had a big drop in the sewer temperature as a result. And obviously that's concerning, but we were able to take a look at this and we had pretty good confidence for a couple of reasons. First, the minimum temperature here is 46, which is not that bad. It's still warm enough to do pretty good efficiency heating and cooling. Second, we were only at 46 for a very brief time. The mean temperature over this excursion was more like 50 or 52, and that, again, is pretty good. Third, the total length of the excursion is quite short. We're looking at maybe 36 hours to get back to the upper 50s. That's not bad at all, right? So we're losing maybe a day and a half of maximum efficiency production. And in the long scheme of things, that's just really not that much over the course of a whole winter or multiple years. And the last point is that when this happens, by definition, we are not at peak heating load for the building because the outside air temperature is in the 40s, if not up to 50 degrees. So when we are seeing a drop off in the available temperature in the sewer, we are not needing as much out of the system as it maybe was designed to produce because we needed that 3 days earlier when the temperature was down below 10 degrees Fahrenheit. At that point, the wastewater temperature was up in the 50s. So it lines up very nicely. By definition, if we are getting cold water into the system, it must be above freezing outside, and you won't be peaking in terms of the thermal energy demand for the building. So we saw these data and we felt that from a temperature perspective, we were in very good shape. And this technology was going to be a very, very good fit. Flow, of course, still has to be assessed point by point. If you don't have the flow available to give you enough thermal capacity for the building, you may not have a project. But from a temperature perspective, we felt pretty good about just about any point in our sewers. I have some additional resources here. When the slides are distributed, these may be references for which you want to go back to. I have some design contacts for the various buildings discussed. I do want to quickly mention the last bit here. The state of Maryland and the District of Columbia have now both passed legislation which recognizes wastewater thermal as a Tier 1 renewable energy resource eligible to generate renewable energy credits under both of those jurisdictions' renewable portfolio standards. What that means is there is a state subsidy for generating energy from this, just as you would get it from, say, wind or solar, thermal, or ground source heat pump, that kind of thing. Massachusetts has an RPS. I'm not intimately familiar with it. I don't know if there are thermal energy resources included, but if there are, it may well be a natural fit to look at adding something like this to it. Certainly, we had good success in both Maryland and DC. I believe we passed unanimously in the DC Council and unanimously in the Maryland Senate, although the Maryland House, we had some Republican opposition, but not too much. So it was a good success there, and I think other states could well look to that as a way to support the growth of this particular technology. That is it for my presentation this afternoon. Looking forward to answering any questions. I don't know if we are doing them now or waiting. I think we said we're waiting, but just let me know, and I'm more than happy to talk now or talk later, whatever you prefer.
Thank you, Saul. Yeah, we're going to actually go through the presentations and have you stay on the line, and then we'll do the Q&A all together. Is that okay, Saul? Okay.
Yep.
Okay.